I'm going to go ahead and get started. So I am going to talk about work that I have done at Fastly, where I'm a principal software engineer, over the past about year and a half or so, developing this tool that we call Weevil, and why it's called that will become apparent partway through the talk. The main goal that we're trying to achieve here is running JavaScript on our platform, which turns out to be a hard problem for a reason that I will now describe. So the setting that we have here is that we run Wasm as a serverless compute platform, meaning that we accept modules from customers and we run them on our servers. And we take HTTP requests. These requests, every request is served by a new Wasm instance. So this is a privacy and security sort of boon. This is an explicit isolation between data that's produced from different HTTP requests. And so this is generally seen as a good thing, but it will cause some problems later, as we'll see. You might think that this is horrifically slow if we have something like an entire JavaScript runtime inside of the Wasm module. We have made this fast with a few different techniques. First, and by we I mean mostly Nick, my colleague, implemented this tool called Wiser that snapshots Wasm modules. The idea is that we can start the language runtime, we can load the program in, and then freeze exactly before we start actually executing the bytecode. And then in the engine itself, we use and develop Wasm time. We implemented this thing called copy on write for the heaps so that the instantiation is really fast as well, on the order of like 5 microseconds. And so that's really good. And then the next thing that is interesting about our platform and our situation here is that we require fully ahead of time compilation. And in our actual distributed system, this is in a separate control plane, right? So this is explicitly isolated in ways for sort of a defense in depth posture. But the main thing here is that we expect to accept a Wasm from the customer, compile that Wasm once, and then from then on, every time a request comes in, we're running exactly the same code. And importantly, we do not give the user any primitives to generate new code or run new code during runtime, right? So this is not, for example, a web engine with JavaScript that one can trampoline through to create a new module. You only have the module that you uploaded. So this is like really great for security and privacy. It turns out that this is also a very hostile environment for fast dynamic language implementations. So in order to understand that, I want to go in a little bit more detail how we actually run code. So we have this technique called Wasm snapshotting. So the idea is that when you have a language runtime, like a JavaScript engine, that is compiled as a program, just an ordinary program, inside of a Wasm module, you can conceptually think of there being two different phases. Even though JavaScript is very dynamic and you can generate new code and eval it at runtime, conceptually there is like parsing and generation of bytecode. And then there's execution of that bytecode, which is a separate phase. And so you could actually think of having two different entry points on your Wasm module. And then you might have a tool, like we've written, Wiser, that would basically take the module and run the init function once, and then create a new Wasm module that has a heap image with the results of whatever init did. And so this is how we produce a new Wasm module that is effectively a compilation of JavaScript. And so from sort of a superficial point of view, we're done. We've already solved the problem. We have a compiler for JavaScript, except not really, because it's still an interpreter inside that's running bytecode. And so there are a few really nice things about this. Again, I come back to security. Wasm is a Harvard architecture, which means that it has a separate code space. There's no possibility of code gen. It's not like x86 where you can jump to random bytes in memory. And it has a first-class call stack that's protected. And so this sort of just rules out by construction a lot of different kinds of attacks. And then again, because we do instance per request, we have this really nice isolation between different executions. So let's go through this list that I made for fun of a JIT engine's favorite activities. All right. So JIT engines really like to generate code at runtime. This is kind of in the name, right? And the reason they do this, of course, is because they observe the program as it runs and then determine only at that late point what code would be best. But you see that that doesn't really play well with the Harvard architecture, right? If we have a separate code space and no code gen at runtime, we definitely can't generate code at runtime. JIT engines also really like to manage stack frames manually and do all sorts of custom stuff with their ABIs, right? So you'll have like order one unwind, where you just set the stack pointer way up the stack when you have an exception thrown. On stack replacement, when you have a new optimized version of a function, multiple entry or return points that have to do with like exceptions or error returns, IC stubs that tail call, all sorts of things that don't play well with the first class call stack that Wasm has. And then finally, even if we could solve the first two problems, so if we could generate code at runtime, say we added some hooks to do that, and say that we worked around all of the sort of impedance mismatches with the ABI stuff, there is this fundamental problem that you need to, a JIT requires observing behavior over time, right? And so if you need to warm up your JIT engine in order for performance to be good, that fundamentally doesn't work with an instance per request model, right? And so we see here that the JIT engine is very sad. It cannot do any of its favorite activities on our platform, at least, which is a serverless Wasm platform with no runtime code gen. And so the straightforward question that you might ask is, well, can't we just add hooks to do JIT, right? So you could add a Wasm host call, or maybe a core feature, that is basically, here is a new blob of bytecode, Wasm function bytecode. Please create a new function, right? Or you could do this today with a JavaScript-based engine where you sort of trampoline out through JavaScript and instantiate a new module and share the memory. And this is actually still perfectly memory safe. It still is perfectly good sandbox because you're running new Wasm bytecode. You're not running native code. And you could also, sort of hand wave a little bit and work around the other incongruities in the ABI. So you could do order n unwind for exceptions. That's not ideal, but okay, it'll work, right? And in fact, someone has done this, which is super cool. So Dmitry Bezhetskov at Igalia has this prototype that he presented a few months ago now in Barcelona at Wasm.io. And it works. And it's got pretty impressive results. So he reported between 2x and 11x speedups. I actually tried to reproduce this. So he told me, first of all, that he didn't enable GC. And so that's one thing to keep in mind when comparing to my results. And then the other thing is I tried to run his patches and they ran into asserts. So I think it's still a little bit in an unfinished state. But this is pretty cool. And if this works for a scenario where you don't have the restrictions that we do with pure ahead of time, no runtime code gen, and pure instance per request isolation, then maybe this is actually the right answer. But the downside, right, is that you either need, as I said, a compiler in the loop, right, and or saving state across requests in order to make that warm up work. Or you could have a sort of PGO-based approach where you try to run the program on test data ahead of time, do profiling. That could be hard, right, though, because first of all, if you do it on the client side, the user might not be able to run their code. There might be different APIs on the client than the server. Or if you do it on the server side, now you as the platform are changing the code in semantically visible ways, and it's sort of a, it's no longer an opaque Wasm module. You have to see into the module, see that it's the engine that you know about, and then actually, communicate with it somehow. And so for both these reasons, we kind of have shied away from this approach. It seems like it's probably not the right strategy to start with. And so let's review the constraints that we have. We're trying to do AOT compilation of a dynamic language, by which I mean dynamically typed, but this could be any sort of dynamic behavior, virtual calls, anything like that. JVMs also have dynamic behavior, for example. And so we can't optimize over time by observing program behavior. So the classical JIT idea is just ruled out, right? Because we start from the same snapshot every time. Yeah, okay, so this is kind of just what I said. We kind of can't do profile guided either because server side we're changing behavior, and client side, it may just not be possible. Okay, but caveat here, at least we can't optimize over time by generating new code, right? We could still learn things during the execution of a single request and have some sort of fast pathing. So I'll get back to that. So yeah, exactly, with conventional control flow. So let's talk about how JavaScript engines today tend to handle the dynamic typing in a fast way. So I'm showing a function body here. It's a function of 2 arguments, returns x plus y is equal to 1. All right, that's just a Boolean, true or false. And so typically, you'll compile this to a bytecode that is almost one-to-one with a JavaScript AST. So it's a polymorphic bytecode. Each of these operators has the same semantics, essentially, as the operator in the source language in JavaScript. And in order to run this, the engine will use what are called ICs, or inline caches. So the idea here is that you could implement the very generic behavior. For example, the add operator, you could say, OK, I have an add. Let me get the two arguments. Are they both int32s? Then I can do the int32 add and rebox it, and we're good. Are they both doubles? Are they both strings? Do a string concat, et cetera. But that will be really slow, and most programs are actually secretly almost monomorphic, even though the language is fully dynamic. And so what engines tend to do is they generate these little stubs that are called IC stubs, inline cache stubs, that are fast paths, right? And so you can basically generate some code that says, if I'm seeing the same case that I saw the last time, I'm just going to do the same thing really fast and return. I'm not going to think too hard. So here I'm showing two examples. Guards are basically checks for certain conditions, and if the guard fails, then we go to the next stub. So if they're both int32s, do an int32 add. If they're both doubles, do a double add. The last entry on the chain is always a fallback that does the generic behavior, and then probably also generates an IC for that new case that we just saw. Cool. So the key idea here is that we have late binding in the execution semantics. Fundamentally, JavaScript, any dynamically typed language, has late binding in the sense that the behavior that is observed at runtime is not determined until we see the types of the values at runtime. We can't know when we compile, a priori statically, at least most of the time. And so that late binding just is translated to late binding in the compilation strategy, right? So we basically say, OK, that's fine. We don't know yet. So let's put indirection in the runtime strategy and have this indirect call. So that's the basic idea of ICs. And so SpiderMonkey, which is the engine that I've worked with on this project, it has actually a fairly nice systematic system, I guess, for lack of a better word, that it uses for IRs. For ICs. It's called cache IR. And so the idea is that it's just a straight line IR with very specific guards and opcodes. It has a few hundred different opcodes, some for really interesting, unique cases. Load the super object, call specific string join, whatever. And the engine has been heavily optimized with the use of these fast paths over the years. So every time we do an update, an upstream SpiderMonkey, we see, OK, someone added 3 new cache IR ops for 3 new cases that they observed. And so we don't want to reinvent this effort. We don't want to invent our own IC system. Let's reuse at least this work if we can. So here's a table of compilation levels in SpiderMonkey, but I believe V8 is pretty similar. I won't go too much into the details, but sort of the key idea here is that there are 4 levels. We can ignore the optimizing compiler for now. We'll get to that eventually, like on the last slide, but that's pretty hard. Generic interpreter is what you would do if you didn't have ICs at all. So that's every case, just check the types and do whatever the types say. And then baseline interpreter and baseline compiler are basically using ICs. The difference is that the baseline interpreter still interprets the JS bytecode. The baseline compiler compiles the JS bytecode to code that just calls the ICs. But in both cases, the ICs themselves are compiled stubs. And so that's actually sort of a problem here. And this isn't really anything fundamental. So this is the first insight of this work, is that that's not fundamental. We could actually get away without compiling ICs. And so the first thing that we thought to do was we have this infrastructure that's generating this IR that says, here are the fast paths. The only reason we can't use it is because we can't generate code from that IR at runtime. Let's just write an interpreter for that IR. And then once we've done that, maybe separately, we can collect all of the known or expected IC bodies that we probably will see, because in practice, they're not an infinite number. Actually, there kind of are. I'll get to that. But in practice, 99% of them are part of a small set. And so we can collect sort of a known corpus, and we can compile those ahead of time and use those. So actually, probably we could have ICs without having runtime code gen. And then finally, the JS opcode compilation is straightforward compared to that, right? So it's polymorphic one-to-one from the original source, and so we can know that without knowing anything about the types or doing any runtime observations. And then we can just compile each polymorphic opcode to an IC site, which is just code that we know how to generate right away. And so actually, like the key insight here, which is pretty nice, is that baseline compilation can be fully ahead of time. It is not currently in SpiderMonkey for boring engineering reasons, but there's no reason that we couldn't build a fully ahead of time baseline compiler level JavaScript compiler. And so that turned into sort of this plan. And so the first part of the plan is that we are going to add an interpreter for cache IR. And the reason that we're doing this and not jumping straight to compilation is that compilation is really hard. Compilation takes a long time to build for me, an engineer. And we wanted to get some speedups sort of in the interim. And so it turns out that like adding an interpreter for cache IR was more or less a summer project. And so we did that, and we got decent speedups. And then let's build an AOT compiler after that. So, OK, the first part is this interpreter. It's called the Portable Baseline Interpreter. Yeah, it's more or less what I said. It's just an interpreter for cache IR. There's kind of an interesting insight that came out of this, though. I was expecting that I would just build the interpreter for cache IR, and I would run the fast paths, and stuff will get faster. That's what fast paths are, right? But it turns out that that wasn't really the case at first, and I was perplexed for a while until I realized that there's an implicit engineering trade-off when you add the fast path. When you have compiled ICs, you can get away with putting more in the fast path than if you have the overhead of an interpreter for the cache IR, right? And so you might say it's perfectly fine to have like these 7 steps if they compile down to 10 x86 instructions in your compiled version. But if you have the dispatch overhead 7 times for those 7 ops, then the IC may not actually be worth it. And maybe the generic implementation was faster in the interpreted case. And so I ended up implementing what was called hybrid ICs, which basically I developed by profiling a bunch of stuff and then figuring out which ICs were actually worth it. It turned out only to be the property access opcodes, get prop, set prop, get lm, set lm, those sorts of things. And then calls specifically because they turn into all sorts of special fast paths for calls to known functions, like string.join, array.map, whatever. And so this has been implemented. It was upstreamed last fall into SpiderMonkey. It's used in production where I work. And geomean of 33% speedup on Octane. Other real customers have seen real speedups, so that's pretty cool. And so here are the numbers from Octane, if anyone cares. So up to almost 2x in some cases. That's pretty cool. So here's our implementation plan. We've done part 1. Let's build a compiler, right? Let's move on to the next step. And so actually, it turns out that we need 2 compiler backends because we have the cache IR, and then we also have the JS bytecode. So I kind of, I'm kind of lazy by nature. I took a step back and I said, do I really have to build 2 compiler backends? And in particular, I just did all the work to get the semantics right, a lot of which weren't that carefully documented, by the way, for the cache IR opcodes and for the JS opcodes. So I did all this work to basically encode this knowledge into an interpreter. I've tested this interpreter. We now trust this interpreter, these 2 interpreters, actually. And then furthermore, if I were to write a compiler from these 2 different bytecodes to Wasm, Wasm itself is actually a lot harder to debug than native systems today, right? So the RR reversible debugger actually came out of Mozilla because debugging SpiderMonkey was so hard. At least that's the folklore that I understand, right? And it's super, super useful to have all of the native debug tooling on a native JIT. Debugging Wasm is extremely hard in comparison. Not impossible, but I really didn't want to put myself in that position. So yeah, and then you have questions around like, well, how do I do unit tests? Maybe I have JIT hooks in a special shell. How do, so debug. And so can't I just like use the interpreters and do something with them? So let's take a step back. Let's look at what an interpreter looks like. It's probably something like this if you squint enough. I'm skipping the loop here, but it's a loop around a switch. And the switch says for each opcode, do something. Say that we have a function that's just 2 opcodes, add and return. What if we just took the code for add and took the code for return and glued them together and called it a day? That looks like a compiler to me. So it turns out that this is basically like a template JIT if you really squint enough. But if you want to get this out of an interpreter, that's a little bit harder. What you need to do in order to make that work is something called partial evaluation. And so the insight that I had here is that, partial eval is extremely hard in general. You really wouldn't want to do this on machine code. But on Wasm in particular, it's a small, introspectable, well-behaved IR. And so partial evaluation actually should be tractable. So let's try it. So let's talk about few-to-more projections, which is what partial eval is in this case. So a few-to-more projection basically says, given that we have some program that takes some input and produces some output, right? This is a very abstract functional model of a program. You can think of splitting the input into arbitrary pieces that we'll call static and dynamic. And so it's actually, the program is actually a function of these two arguments, static and dynamic input to the output. And you can, for an interpreter, for example, maybe the static part is the program it's interpreting. The dynamic part is the actual input to the program that's being run. And then just curry the program with the static part, right? So p-eval here is basically just, currying from functional programming or just constant propagation if you want to think in terms of compiler passes. That program, namely the interpreter, with that static input, namely the program it's interpreting, and that should give you some modified program that then run just on the remaining input produces the output. Right, so the first part here, the first top level bullet is just saying function currying works. So if we do currying with an interpreter and the text of a program, we get a compiled program. That's called the first few-to-more projection. It turns out that in this beautiful 1973 paper, few-to-more also described the second and third few-to-more projections, which I won't go into here. The second few-to-more projection is actually a nice way to get a compiler without having the partial evaluator left over. And the third is even wonkier. It gives you a compiler. The second and third, I think, are really hard. I have some thoughts on that. Probably can't be done in Wasm. But the first might be tractable. So Weevil is a partial evaluator for Wasm. And the key idea is that it produces specializations of functions in a Wasm module with respect to some constant inputs, namely bytecode. A very important guiding principle here is that there's no magic, or at least as little magic as possible. So, early sort of fever dreams of this idea started with, maybe I can recognize the shape of an interpreter loop, and maybe I can do special things to pull out pieces of it and glue them together, kind of like I sketched in an earlier slide. But that's, I think, a losing proposition, because then you have to sort of debug not just an interpreter, not just a compiler, but a program that is playing a compiler in a trench coat by pulling apart an interpreter into pieces and putting it back together, right? Like that's not going to be easy. And so instead, let's think about semantics preserving transforms, where we take a Wasm and we produce a Wasm that does the same thing. And we take a Wasm function and we produce a Wasm function that does the same thing. As long as we hold that principle, then things will be a lot simpler. And so it turns out that, like, if we do this, we get a compiler for free once we have an interpreter. Now, for free is doing a lot of sort of like heavy lifting here. I spent a year, almost a year and a half, working on this. That's amortized cost, so this will work for other languages too. I still think it was the shortest path I could have taken. But once we have this, like, we basically have the single source of truth, which is the interpreter, and we get a compiler out of that. Those of you who have read the PLDI 2013 papers will remember Graal VM. And so this is certainly related work. It's a lot like Graal. Two distinctions. One is that it's a heck of a lot simpler because we don't try to do JIT. There's no dynamism here. No like dynamic deopt, nothing like that. And then the other is that Graal required you to use its API and its AST classes. We want to start with a general pre-existing interpreter. So we don't want you to have to write your interpreter for Weevil. We want to just take an interpreter because we have one, right? Namely SpiderMonkey, and we have others as well that we might, Ruby, Python, whatever. And so let's work with that. And so sort of the entry point here for Weevil is that, say we have some function called call function, and this is like an interpreter, right? So it calls the interpreter on F bytecode, and let's just say that every function has two arguments, two ints. What we need to do, instead of having just this runtime behavior of calling the interpreter, is we need to have a phase separation. So we need to first say a function has been born somehow, right? So we parsed new code, whatever. We have a new function. We're going to call this intrinsic, Weevil, and we want to tell it to take the interp function and create a specialized version of it, stick it in func pointer, with the bytecode parameter as constant memory, right? So we have to promise that that memory is constant. It's not going to change at runtime. But the two other parameters are runtime parameters. And then once we have done that, then when we go to invoke it, let's check func pointer if it's not null. If it's not null, let's call it. Otherwise, we can fall back to the interpreter. And so sort of one key aspect that makes this work well, or makes this work at all, I should say, with our deployment model, is that it's asynchronous. So we build on top of Wiser snapshotting. So we don't have Weevil in the loop, Weevil and all the compiler and everything, where the engine could say, please specialize this function. OK, I have the func pointer as a return value that I can call right away. Rather, we sort of load all the code, let it be parsed, let all the Weevil requests accumulate, freeze the module, and then fill in all those function pointers in a batch, and then regenerate the module. So that asynchrony is important. But other than that, the specialized function must behave exactly the same as the original interp function, and that's sort of the linchpin of our correctness here. OK, so are we done? Is that it? Do we just like const prop the function and call it good? Not quite. If you Weevil just this function, it will indeed constant fold PC to whatever constant address, but you'll still have the loop in there. And so this gets back to the magic or not quite magic distinction. It would be a little too magic to try to recognize the shape of loops and determine this loop is a loop that's the interpreter loop, this loop is some other loop, or do something terrible with every loop and blow up the code size. Instead, I came up with this idea of context sensitivity for specialization. So the idea here is that we need to annotate the interpreter. So this is pretty much the only annotation you need, but we do need these annotations to say, we now want to continue our constant folding in the context of this particular PC value. Right? So if you think in terms of like meet over all paths, constant folding, classic data flow analysis, if we just have an interpreter loop, we'll start with PC constant 1, and then we'll have a back edge, and that goes back up to like PC constant 2. So now we have 1 and 2, and that meet in the lattice to just runtime. And so we can't say anything anymore. PC is not constant. But if we say that in this particular context of PC1, PC is constant 1, and then that branches to a new context where PC is constant 2, so in that context, PC is constant 2, et cetera, sort of we split out all of the different instances of the interpreter loop in the constant folding. And so this ends up allowing constant folding to basically do that pasting that I illustrated earlier. And so again, the key thing here is that there's no magic. There's only expanding code where we add new context. That's it. So I'm going to show an example of how this actually works. So here's a CFG. This CFG is a cartoon sort of sketch of an interpreter. Block 1, V1, V2 are probably like loads of the opcode. Then there's a switch this would be a BR table in Wasm. It's like to different opcode implementations, and they come back to some tail, and then there's a back edge for the loop. So Weevil requires the following state, the Weevil transform. So from the generic function, we're creating the specialized function on the right. We keep a map of a context block pair on the left to a block on the right. So we basically say for every block on the left, we may have a block in a particular context on the right. Likewise for SSA values. For every value on the left, for a particular context, we may have a value on the right. This probably will be quite sparse. In fact, it should be if we don't want this to blow up. We won't have a copy of the entire interpreter for every context. And then we have just a work queue. So this is a work queue-driven algorithm where we basically say we need to const eval this block in this context. So yeah, and then for every block, we do sort of the classical cprop thing and branch folding. So we have a lattice, which is top or some particular value, or bottom, which is runtime. And then let's track context itself as part of the flow-sensitive state and update with the intrinsics that I noted. And then at branches, enqueue the target. So if we update PC from constant 1 to constant 2 and branch back to block 1, then we'll get a new copy of block 1 for PC 2. So say we start at PC 0. We'll start with the work queue with the entry block in that context. We'll have a copy of that. Because we have a constant PC, we can const eval. And because we said that the bytecode memory itself was constant as well, we can const eval the load from bytecode memory to say, oh, that's just constant 3. Our opcode is 3. And then we can branch fold that switch. Instead of having the dynamic choice of all the different opcode cases, we say, I know that it's opcode 3, so I'm going to take block 5. And so we have block 5, block 6. We basically just paste in a copy of that opcode implementation. And then, probably increments PC and updates context and goes back to block 1. And so we have a new context to make another copy of block 1 in that context. Really cool thing that sort of just fell out of this is that say that we have bytecode that has a loop in it, right? Or any control flow that's not just a straight line. The branch back to PC0 will look up in this map that I showed from the context block to the specialized block to see, do I have a copy of block 1 in PC0? So it's not going to be like a tracing, JIT or something like PyPy style, where it traces through and gets another copy, yet another copy of block 1. It's going to say, oh, I already have a copy of that block, so I'm just going to generate a branch back to it. So this is like sort of the mind-blowing outcome of this. The resulting CFG that we produce in the specialized function is, so I'm using this word loosely, convolution. It's kind of a combination of the two. It's a convolution of the interpreter CFG and the bytecode CFG. So think of the bytecode CFG as a skeleton, and then we're taking copies of the interpreter loop and sticking them in for every opcode, branch folded. So that's super cool. At least I thought so. There's some notes on SSA here, which actually I'm not going to get into for time reasons. But like you have to be a little bit careful about the DOM tree. And the other thing that you might want to do is I lied a little bit when I said no more intrinsics. You might want intrinsics to lift accesses to registers and or the operand stack, if it's a stack-based VM, to SSA. And so Weevil has intrinsics for both of those. Cache IR is a register-based IR, and the JS bytecode is a stack-based IR, so I have intrinsics for both. And then there's a little bit of care taken with switch because you need a constant PC for that to work. This basically just says that the interpreter actually has to have a native or a WASM level frame for every interpreter frame. So you can't do the optimization where the interpreter says, okay, call opcode is push a virtual frame and just continue. You actually need to do a call at the WASM level because that's how the specialization is mapped. And then, yeah, so you can do other tricks. I'll skip through it. ABI stuff, optimizing through WASM time as well, add an optimization for call indirects. Here are the results. So those of you who were also here at CMU when I was here 6 weeks ago saw these numbers. It's gotten better in the meantime. I included them just for that context. But sort of the headline number is that on some benchmarks, it's a little over 5x, or almost 5x. It's between 2 and 3x on every benchmark, faster than the baseline interpreter, or faster than the generic interpreter, and a geomean on Octane of 2.94x, almost 3x. So I'm pretty happy with this. I think we're basically going to ship it. I had wanted to get a comparison to the sort of direct JIT approach to see like what overheads remain. And I mentioned I tried to get that to work. There are some weird assert failures. I haven't gotten a response from the authors. But this is a pretty good speed up. So we're pretty happy with this. The native baseline compiler, by the way, gets between 5 and 6x on the same benchmark set. So there's still some more, not low-hanging fruit, maybe medium to high-hanging fruit here. But it's still pretty good. And then the part that I will sort of like signpost but not get into in detail for time reasons is that we have a plan for the optimizing phase as well. And the idea here is PGO-based, but do it in a semantics-preserving way. So Nick actually also wrote this tool called Winliner, which basically profiles indirect calls during WASM execution, and then inlines, speculatively, with a guard, the most likely call target. And so the idea is that if you have IC sites that are just indirect calls, you effectively get the IC inlining approach to optimizing compiler, which is also what SpiderMonkey native does with Warp Builder and WarpMonkey. And then you can have other sort of generic optimizations that, from first principles, hoist and remove guards and box-on-box pairs. So the sort of thing I want to like highlight here and maybe put a bow on a little bit is that we're definitely playing on hard mode, but we're trying to derive a JIT from first principles, from an interpreter, right? And there are a few reasons for that. One is that interpreters are easier to write and debug. In fact, when I developed Pebble, the interpreter mode, I actually did almost all the development on native, and I used RR to debug it. And that was a whole lot easier than debugging on WASM. Unfortunately, we should fix that story. But And then also, interpreters are separately useful, right? So like, you might want interpreters for cases when you have dynamic code that's been loaded that you haven't been able to compile. You might want them sort of, as we did for like, software release timeline reasons. And then finally, principled transforms are actually easier to test. So the way that I tested Weevil is with lockstep execution of the original function to the specialized function. And that's a lot easier to reason about than sort of an ad hoc compiler that's emitting bytecode that I have to manually correlate and verify. And so the last thing I'll highlight is that we aren't doing anything special that is language specific or JIT engine specific, actually. So I upstreamed one optimization into Wasm time, but that's not necessary. So like, that's actually reusable for other languages as well. After I gave this talk last month, I was talking with a grad student somewhere else, and they're currently curious and looking at applying this to C Python. We also wrote a toy interpreter and applied it. So this could be applied to other languages as well, not just JavaScript in SpiderMonkey. So yeah, that's all I had to say. Are there any questions?
For Chris? I'm going to give that man a microphone.
Awesome talk. I need to remember my questions. First one, do you think you could go back to the CFG of your combined Weevil output?
Yeah.
I just wanted to clarify something real quick. So is it still a loop? Because I think normally when you have a template JIT, like the main performance driver is that you're completely eliminating the dispatch loop. Is that literally a back branch in your output?
Yeah, so that back branch is coming from this PC1 go to 0. So this back edge has disappeared. In effect, in context, it became this edge between block 6 and block 1 here.
Oh, I see. Okay.
And it became this edge. So I guess technically that is a back edge, but it's a back edge because this was a back edge.
Okay, so it's literally like, okay, so I have some. So when you say PC0 and PC1, those are like bytecode 0, bytecode 1, and you're threading them together. Okay.
Yeah.
I guess another thing, so you're talking about an optimizing compiler in the future. Have you heard of Hop at all? They have a strange loop talk, I think. I haven't looked into them in too much depth, but basically, as far as I understand it, they're like a really good ahead of time only JS compiler, so It might be worth looking into. I imagine it's a really big task to actually adapt anything from them, because I think they compiled a scheme first. But it's probably worth looking into. I'm sure they have some interesting optimizations.
Awesome. Take a look. Thank you.
Did I have anything else to ask? Oh yeah, this is a really callous question, and it's like super cool. I don't mean like this. Like I think the endpoint here is like super awesome.
Yeah.
Why did you go for this approach over just a template JIT? Because it seems like you have the bytecode to start with, and you can output Wasm at that stage.
Yep.
So it seems simpler to me. I mean, obviously, you don't get to reuse the interpreter. Is that like the main reason?
Yeah, well, so that is a really good question. I ask myself this a lot, too, in my depths of debugging hell, and others have asked me this a lot. So the honest reason is that I do, with all of my hindsight, believe this was the fastest path. I think that it would have been a lot more debugging hell to get a direct to Wasm template JIT working. I think that, I mean, so like the Igalia folks are essentially doing that approach, right? And Dimitri, great, really smart guy. He basically determined that so there's the macro assembler in SpiderMonkey, and so he's basically like building a new Wasm implementation of the macro assembler. So I think that approach is like pretty straightforward, and like from a systems complexity point of view, that's probably actually simpler. Except that getting to full correctness is still just like, I think, a much bigger climb than, okay, I can debug the thing, and I can, this also might be my bias. I'm a compiler person, so I can think about compiler transforms and say, I can see why that transform is correct. It's much harder for me to debug a thing that I can't attach a debugger to.
Right, yeah, I think that makes sense. Yeah. Awesome, thank you.
I got a question. So you mentioned that you think that Fudamura projection, the second one, might not be possible in Wasm. On the surface, it seems like if you have the partial evaluator as one giant Wasm function, you can do that.
So I've thought about this. Yeah, so in Weevil in particular, the main loop is not just a simple loop. It's a work queue-driven loop. I think if you squint hard enough and you think about symbolically interpreting a Rust vecdeck in the heap during the constant propagation, maybe it's possible. Probably there are better ways of doing that. But like, I think that the hard part is really the control flow. So the reason this works at all is that we can essentially run the interpreter loop in like linear mode, PC 0 through n-1, because the control flow in the interpreter is simple enough with the intrinsics. And a more complicated data flow, iterative data flow driver loop, I think is just, it's hard to fit into that. So this gets to, I think you asked a question last time I gave this talk about SSA and CFG. I think that if you had an AST and if you reformulated this as like a direct AST transform, a single pass transform, it might be more tractable. I haven't thought too much about that, but that's like an intuition. Yeah.
Hi. I'm not sure if I understood correctly, but you have this kind of annotation sprinkled through the interpreter with these weval update or weval context, update context things. So that's actually code that has to be inserted into the interpreter. So I'm trying to understand the role of this, right? So you could imagine you have this on every single line, and then you could just say, well, then you don't need it, right? Because then you can just assume that it's there. But I assume that maybe your state space blows up too much, or the other thing I wanted to ask in relation to this is, if you had written this interpreter loop as tail recursion, and you think of sort of the update call as your recursive call, right? And you could sort of get this out. In other words, is this annotation basically just giving a hint to the translator to say, here's the place where I would have made the recursive call?
Yeah, I mean, it's certainly the place where you have, in this case, the back edge in the interpreter loop.
Right,
so I think that, so why not, two related questions I think are, why not have it implicit, just know the PC variable, or why not have it like more frequent than just at the back edges? The latter I think is perfectly fine. It's an intrinsic, it updates the flow sensitive state, and so if we update it to the same constant, nothing bad happens. Having things more implicit I think scares me, because then one, I can't reason about it, and two, it puts sort of more brittleness in the critical path. So
I imagine it's very easy that it blows up, that you have that something gets taken into the context that is just not bounded, and then you don't count it.
So the thing to be careful about here, and actually Ben also asked a related question last time, is if you have the wrong PC, right? So say you have like, you set the actual PC value to 4, but in one case PC context is 4, in the other case PC context is 5. It'll still be a correct transform, because all we're doing is adding context. And so in essence, like the lattices don't lie, right? Like we'll go to runtime. But we'll get like a copy of the entire interpreter switch rather than just the single opcode if we go to runtime. So one thing that I did to make this a little less brittle is I also have an intrinsic that's assert this thing as constant. So I basically update PC, set the PC context, and then at the top of the interpreter loop, assert that PC is constant. So I just force a Weevil error if we ever get that case where we would copy the entire thing. Yeah. I guess I missed the tail call case too. That's interesting. I haven't thought that much about it because I think in terms of CFGs. I think if you were doing CPS, then maybe that would be more tractable. Everything here is single function. So that's, yeah.
Hi, amazing presentation. Thank you so much. I was wondering if there's any limitations on the WebAssembly that weval can run. For example, like Wasm GC.
Nothing fundamental. The only practical limitations are that I'm using my own decompiler and compiler library called Waffle, just like Walrus, but SSA. So I just need to add support for whatever proposals. I added Wasm SIMD recently, so no reason GC couldn't be added.
Thank you.
All right, thanks.